Okay, so today we're going to start the fun part of the course, at least for me. What we've done so far has been really setting up some basic examples and techniques to get used to studying some dynamical systems. And today we're going to start some class of systems that I think become much more interesting. And we're going to introduce the third method of to study the topological conjugacy classes, and this is called symbolic coding or symbolic dynamics. So to introduce this method, I'm going to start by studying a particular map, which seems a little bit artificial at the moment, but as we shall see, it's much more general. So let me define this map here, a map from R to R, defined like this: f of x is equal to 3x for x less than or equal to a half, and 3 1 minus x for x greater than or equal to half. So what does this look like? So you notice when x equals 0, so these coincide actually. When x equals a half, then this is 3 halves, and this is also 3 halves, right? So when x equals 0, this is 0. When x equals 1, this is 0. So here we have, let's put it here, 0, 1. When x equals a half, this is 3 halves. And then it's just straight lines like this. So this here is 1, and this is 3 halves. This is the graph, okay? Okay, this is just an example which we're going to use to try to introduce some techniques. So let's study a little bit the dynamics of this map. So does it have any fixed points? This is always the first step, yes? The fixed points, this is the graph of the map. So the fixed points is, so let me actually So two fixed points, 0 and some fixed point P, which is where the graph intersects the diagonal. Okay, that's easy. What happens if we start with a point that is here, negative? Okay, so remember the way we graphically do the map. So because the graph is below the diagonal, then that means that it's going to go to the left, right? So you look at the image is here, and then the next, which when you project along the diagonal gives you a point here, and then you do the same. Okay? So what is the first observation? This holds for any point that's negative, right? So we start analyzing the situation a little bit. So if x is negative, okay, this implies that Fn of x converges to minus infinity. Yes, because they just move. If you start with any point on the negative, then it will just move away. It will converge to minus infinity. What happens if x is bigger than 1? Take a point here. Then its image is negative, right? Because the graph is below the x-axis, so its image is negative. So that means that it's next. So again, so this point here is just, well, it's just the same point here, which means it maps to here. which means that it also maps to minus infinity. Okay, so all the points bigger than 1, after the first iteration, they map to something negative, and then they move to minus infinity. So x bigger than 1, also fn of x goes to minus infinity. Okay, so the only interesting things that may happen, if there's anything interesting that happens that we don't know, will happen in the interval 0, 1. Because everything less than 0 goes to minus infinity, everything bigger than 1 also goes to minus infinity, and nothing interesting happens. So let's focus on the interval 0, 1. We know that there's 2 fixed points. Are these attracting fixed points? Are they? What's the derivative? Is it bigger than 1 or less than 1? Bigger than 1. Okay? So they're not attracting, they're repelling fixed point. If you take a point near 0, it will move away. And the same here. If you take a point here, it will move away from P. Okay? So we will try to understand later, a little bit later, the global picture. But first notice that there's something interesting. So if you take a point in this interval 0, 1, does its image remain in the interval 0, 1? Always? What about the point 1/2? What's the image of 1/2? It's 3/2. We just calculated it. So the image of 1/2 is 3/2, and 3/2 is less than 1. So the image of 3/2 is negative, so it will go to minus infinity also. Yes? So if x equals 1/2, implies what? That also fn of x tends to minus infinity. Right? 1/2 here, it goes here, it goes down here, and it goes negative, it escapes. This point, in some sense, they escape the system, they leave. What about points very close to 1/2? Same thing, right? So there is, in fact, the whole interval, all these points here, the open interval, any of these points, its image is bigger than 1. Okay? And so once it reaches bigger than 1, then we know that when you iterate further, it will go to minus infinity. So we have here not only that, so if there's anything interesting, it happens between 0, 1, but we see that some points in 0, 1 can escape. Okay, like these points here. All the points. Which points are these actually? In this particular case, we know exactly what these points are. What is this point here?
1/3.
1/3 and 2/3. Okay, so for x, in fact, inside the open interval, 1/3, 2/3, these also escape to infinity. Are there any points that escape to infinity? Like, there's a lot of escaping going on. What about these points here?
Actually, I think there is a, for example, from 1 to 9 and to 1 over 9 and 2 over 9, and the image of is inside of the 1 over 3, 1 over 3 and 2 over 3, and again.
Exactly, right? So the pre-image of this interval. So now, if you look at this interval here, this is 1/3, 2/3 is here, right? So all the points that map into this interval, they also escape. So here you can see that if you look at this interval 0, 1/3, it maps onto the whole of 0, 1. Right? So of course there is an interval in the middle, which you could, in this particular case, we can calculate explicitly. It's 1/9, 2/9. But the important thing is that there's an interval here in the middle, which maps exactly onto 1/3, 2/3, and therefore this interval escapes, right? So we have here, we have an interval that escapes. Here also we have an interval that escapes, and also on the other side, obviously, right? So you have also, here also you have this interval 2/3, 1. If you see from the graph, it maps bijectively onto the whole interval 0, 1. So there is some interval in the middle. So this on this side, it does not contain the fixed point because of course the fixed point cannot escape, right? So the fixed point is fixed. So here there's another interval of points which map to 1/3, 2/3. What next? Again, the same. Okay, we'll see what's happening here, what we're constructing. So, is there anything that's left? At this point, we start asking, okay, what's left? You know, does everything eventually escape? We know there's two fixed points. Okay, so those do not escape. So let's define let's define a set of lambda to be the set of points x such that fn of x belongs to 0, 1 for all n greater than or equal to 0. So this is the set of points that never escape. Okay, because we know from this analysis that if at some point you leave 0, 1, then you never come back to 0, 1, you just escape to minus infinity. Okay? If we want, we could also write the set of points that never enter the interval 1/3, 2/3. Okay, but essentially it doesn't matter, it's the same thing. So this set is non-empty because it contains the fixed points, at least. Okay? We don't know at the moment exactly what other points it contains. We're going to try to study this. Okay? What we do know is that if x is in lambda, what does that imply about f of x? It must also be in lambda, clearly, right? Because if the orbit of x stays inside 0, 1, then clearly the orbit of f of x also stays inside 0, 1, because it's just a point on the same orbit, right? So this is also in lambda, okay, i.e. this means that f of lambda, that lambda is invariant, right? So f of lambda maps into lambda. It's an invariant set, a forward invariant set, okay? In fact, we will see that f of lambda is actually equal to lambda, but for the moment we just make that observation. So we want to study two things. So the fact that it's an invariant set means that there is a well-defined dynamics restricted to lambda. So we can say, okay, look at lambda and look at the dynamics on lambda, right? Every time invariant sets play a crucial role, because an invariant set means that you can kind of look at the dynamics on that invariant set, because you take a point on that set, it stays inside that set, so you can analyze what is the dynamics, okay? And that will give us a complete picture, right? Because any point that is not in lambda eventually goes to minus infinity. So if we can understand the dynamics on lambda, the structure of the set lambda, the dynamics of lambda, we basically understood the dynamics of all the possible points in here. Okay, so what is our strategy for understanding the dynamics on lambda? Actually, let me write the theorem, maybe. Maybe I will write the theorem. So, theorem that we're going to prove is that lambda, the structure of lambda is that lambda is a Cantor set, as some of you recognize. And so in particular, this means that it's got a lot of points. How many points are in the Cantor set, you know? Uncountable. Cantor set is uncountable. It's part of the definition of the Cantor set. Okay? So periodic points. So the set of periodic points of f restricted to lambda so this is the set of this is f. Since lambda is invariant, we can talk about f restricted to lambda, so we just look at f on lambda. So this is the set of periodic points, is dense in lambda. So there's lots of periodic points. Okay, as we shall see, there's periodic points of every possible period, which if you just look at the map here, it's not obvious at all. We've got these two fixed points. It's not at all clear how we're going to get these periodic points out of here. Okay, and there exists and f restricted to lambda is transitive. I can't remember if I defined formally transitive for you.
No, but we defined in tutorial.
Alright, so transitive means it has a dense orbit. Okay, so it's transitive, so there exists x in lambda such that, let me write it like this, such that omega x equals lambda. Okay, that's another way of saying that it has a dense orbit, because the omega x, the omega limit set is all the accumulation points, and saying the every point in lambda is an accumulation point, so that's the same as saying it has a dense orbit. Okay, so this is the theorem. In fact, our technique will give us much more information. It will give us really very, very detailed information about the structure. These are just the main properties. And I just want to emphasize how kind of surprising it is, okay? Because you look at this, and how do you see, by looking at this construction, you can kind of see that you're going to get a Cantor set in some sense. Okay, this is a little bit, I used 3 on purpose. Okay, because you get the kind of standard Cantor set. Of course, we need to ask whether if you change what happens, as we shall see, this does not depend on the fact that we have this very specific map. As you see from the construction, we could take anything bigger than 2 here, and it will give the same basic picture and the same conclusions. Okay, we will see that later when we generalize. For the moment, we'll use this. Okay, so how are we going to prove this theorem? Okay, the first observation is this, that let me give some names here. So here we have these two intervals. So write I0 is equal to the interval 0, 1/3, and I1 is equal to the interval 2/3, 1. Then lambda is equal to the set of x such that fn of x belongs to I0 union I1 for all n greater than equal to 0. Do you agree with this? So when I wrote the definition of lambda, I said fn of x is in the interval 0, 1 for all time. Okay? But I could just as well write that fn of x is in the union of these two, because if it's not in the union of these two, then it means it falls in here, and then it means it falls outside. Okay? And the reason I want to write it like this is because I'm going to use the fact that if you take a point that belongs to lambda, every iterate is in I0 or I1, and I want to keep track of which one it is. Okay? So I'm going to define now the sets. let a bar equals a 0, a1, a2, a3, okay, be an infinite sequence with ai either 0 or 1. Just any infinite sequence of zeros or ones. Okay? And then let I a0 to an be equal to the set of x such that f I of x belongs to I ai for all I from 0 to n. So let's think a little bit about what this means. So for every n, okay, so for all n greater than or equal to 0, let x. Okay, so I have here a sequence of zeros and ones. So let's check. For n equals 0, let me write some examples. Okay, this is the definition. So now, examples. So for n equals 0, we have I of a0 is equal to the set of x such that this is just I equals 0. So x belongs to I ai, a0. What does that mean? Exactly, it's either I0 or I1. Right? So this is a sequence of zeros and ones. So I could take a specific sequence. A0 is either 0 or 1. Okay? Depending on whether I0 is 0 or 1, I0 is equal to the set of x, which is x is in I0. This is a kind of trivial identity here. And I1 is equal to x such that x is in I1. So this definition here coincides with my definition of I0 and I1 in the case I equals 0. Okay?
But can we check the case when I equals 1?
Excuse me?
Sorry, sir. If we check the case when I equals 1.
When n equals 1?
I.
Yes, so at the moment when n is equal to 0.
When I equals 1.
Yeah, so now to do that you need to take n equals 1, right? Because when n equals 0, then you just have I equals 0. This is the only part in the definition, right? So now, so how many of these how many possibilities are there? This is equals I0 or I1, okay? Depending on whether A0 equals 0 or 1, whatever that is. So what about if n is equal to 1? Okay, then what are the possibilities? Then we have I of A0, A1 is equal to the set of x such that x belongs to I A0 and f of x belongs to I A1. So what are the possibilities? E.g., suppose A0 equals 0 and A1 is also equal to 0, for example. Then what is the set? Then we have I00 is equal to the set of points x, where x is in I0 and f of x is also in I0. What set of points is that? So you look at the points in I0. So this is our I0. And this is our I1. You know what? Let me redraw the picture cleaner, because this is a bit messy. And let me just restrict to the part that we're interested in, because it's a bit easy. So this is 0, 1. Okay, this is 1/2. And this is the picture that we've got. Okay, here we have it continues, but we don't really care what happens here. So I want to draw this picture also because, as we shall see again, preparing also for generalization. The fact that this is exactly 1/3 or 2/3 or what happens outside doesn't really matter that much. Right now we're concentrating on here, but this, since we do have this specific choice, let's put in the numbers. So let's call this delta is equal to 1/3 and 2/3. Okay, this is delta here. Points that fall in delta, they escape, right? And now this is I0, and this is I1, right? These close intervals. So what happens to the points in I0? Here we want to know the points in I0 whose images are also in I0. And then we can define 0, 1 is equal to the point x, such that x belongs to I0, and f of x belongs to I1. These are the two possibilities with 0. And then similarly we have I10 and I11, right? There are four possibilities of this, okay? So you can have 4 combinations, 0, 0, 0, 1, 1, 0, 1, 1. Okay, so let's look at all these 4 combinations, what they actually correspond to here. So we have the points in I0. We already saw what happens to the image of I0. I0 maps to all of 0, 1. Right? So let's look at what happens here. So here we have the diagonal. Okay, now we have delta. This is delta, right? This is again the set of points which are bad. And here we have I0, and here we have I1. So I didn't draw it really properly to scale, but this is I0, this is I0, this is I1, this is I1, okay? Okay, so now we look at the points in I0, and which are the points whose image lies in I0? It's this, right? So this is exactly I00. And where is I01? It's this, right? It's this here. These are the points that belong to I0, and their image is exactly I1. Okay? And the same thing on this side. So here we also have, we look at the image of I1, it maps onto the whole thing. So now there is, so here, these are the points that map to delta, so they escape. And what do these points do? I11, right? So this is I11 because these are in I1, and the images are also in I1, and this here is I10. Okay. So we have seen exactly these four possibilities for A00, A1. So these are the possibilities here. I kind of said that we had fixed one sequence, but now we're looking at what you get with all the different possibilities. Okay, so whatever the sequence is, there's 4 possibilities for the first 2. Right? So if you look at A0, A1, there's these 4 possibilities, and notice that lambda is contained in the union of all these. Okay? lambda, notice that is contained in the union of I00, union I01, union I10, union I11. Why is that?
Because outside, if outside of, I mean, complement of this set is of course the information is, I mean, after some iterations we can take outside of one.
They escape. They escape, exactly, right? So because because basically these are the only possibilities, right? If the point does not belong to either I0 and I1 and its image does not belong to I0 I1, then it means it belongs either X or its image does not belong to the union of I0 and I1, and therefore it means it escapes. Okay? So we are narrowing down. In some sense we are saying, okay, we are kind of doing the next step of the procedure where we know that the set lambda cannot be in delta, so it needs to be in the union of I1, I0 and I1, but we go one step further and we say, wait, but it also cannot be here or here, and the remaining four components, there are four components, and they are kind of characterized by this property, I00 and I01 and I11 and I10, and so lambda needs to belong to that. Okay? What about with 3? How do we proceed? Let's do one more 3 and then we kind of look at the general case. Right? So, what about I, A0, A1, A2? How many possibilities are there? 8 combinations of zeros and ones. Where are they going to come from? So, when you fix each of these, then there's only 2 combinations left, right? So for each of these 4 cases, basically you then have a choice whether to put 0 or 1 in the third place. Okay? So where is it going to be? Let's take, for example, this one here. Let's take this. So this here is I01. Okay? And then we have a possibility here. We have I010 or I011. These are the 2 possibilities in the third place. And these must be subsets of this. Why must they be subsets of this?
Because the only one contains those who start in 0, the first iteration.
Exactly, because the definition says that what this means is the points where x is in I0, f of x is in I1, and f2 of x is in I0. And this one is f of x in I0, x in I0, f of x in I1, and f2 of x in I1. So they include in their definition already the fact that this, and they add an extra condition about the third interval. So this is subsets. So what subsets are they? How do we figure out what subsets they are?
We have to project, for instance, this small interval, which is between I00 and I01 into the MTH, and we should notice that the points in I01 cannot lie in this projection. Do you understand?
No, I did not follow exactly.
Okay, just make clear that first we have to project this small interval, the forbidden one, between I00 and I01.
Or you want to take the pre-image of this?
Yeah, no, the between.
Here?
No, the other one.
This one?
No, the small one.
This one?
Yes.
Yes. What do you mean by project?
Yeah, just put that one in the y-axis.
Oh, put this one on the y-axis. Yes, yes, yes. So we have the image. So that's one way. So there's several ways to see this. Okay, so this is that. So one way to see this is this: is that of course this image, we know that everything that falls in here escapes. Okay, so we have this on the y-axis, and we have also the image of of we have this okay.
The other way, far right to
In between I11 and when I10.
to the right, to the right.
Yeah.
Yes. Sorry, I was getting confused with this. And this one here also. So these two are the intervals.
No, but here we missed the part, right?
Sorry?
This part is also gets mapped by the symmetric part to the right. So there's I0, we have to extend the two lines until we reach the end of the square. You draw I0 on the y-axis, right?
Yes.
So
This is I0.
yeah, the small part in the middle that you just draw. This part, you have to extend the lines to the end of the graph, right?
You mean to here? Well, they happen to coincide. Because this picture is very symmetric, they coincide. So in fact, the picture is not symmetric, is not correct here. Because this should be... because I did not draw the small ones. So here there's... wait. I didn't draw the picture very well. What's happened here? So I've got this middle one maps to here. And then, oh yes, and then I've got the pre-images, which are these two pre-images here. So you're right, these two pre-images, but then...
We have to find pre-image of
Again, and this pre-image, the one I told you, the pre-images.
So really, I guess this should have been here. Yes.
So there's two parts.
Let's do this separately. I did not draw the picture very well, so you cannot see. But it doesn't matter, because actually we don't need this symmetry, okay? Because this symmetry is not necessary, okay? All the construction we will do would work if we have something like this. If we have like one thing like this, and then one thing like this. Okay, we will do this generalization, but I want to take this opportunity to tell you that we do not need the symmetry between the left and the right. So let's just look at one side at a time. Okay? And let's just look here, indeed as you say. So so this is I01. Okay? And I01 maps to I1. Right? And inside I01, so maybe because maybe let me write down the formal let me write down the proper way. In the end, we need to have an induction to go from one step to the other. So let me write down the inductive step, and then we will verify it in this case. Actually, I think it's easier. So let's write it like this. Let me write this lemma the way we have it. Lemma is that for all A bar equals these sequences A1, A2, okay, AI 0, 1, and for all n greater than or equal to 0, we set I A0 to AN is a non-empty closed interval. Because we're getting a little bit too confused with these pictures. So, okay, so we have verified it. So we're going to prove this by induction. And then we will check this case n equals 2 in the induction. So, by induction, what do we have by induction? So we verify it for n equals 0. Okay, so 2 for n equals 0. And for n equals 1 also, we checked it kind of directly, okay? And what is the inductive assumption? We need to add, for the inductive argument, we need to add also another condition, assume also inductively that f f n from I a0 to a n to 0, 1 is a bijection. So the inductive assumption, sorry, I'm not being enough systematic. So assume inductively that the assumption is true up to time n. Okay, assume inductively that I a0 to an is a non-empty closed interval. And that Fn from IA0 to An to 0, 1 is a bijection. Okay, so in particular, we assume inductively is an empty closed interval. So how does the induction proof work? First of all, true for n equals 0. Right? What is the situation for n equals 0? For n equals 0, we've just verified that we have I0 and I1 are non-empty closed intervals. And f I0 have I got the indexing right? So this should be n minus 1. So for n equals 0, f n plus 1. Yeah. Okay, sorry. So for n equals 0, we have I0 and I1. I should have probably called this n equals 1. The indexing is not ideal, I'm sorry about that. f I0 to 0, 1. And f from I1 to 0, 1 is a bijection. Do we agree with this? Yes? This is just the assumption, okay? This is just the setting of the map, which is I0 maps to 0, 1 bijectively, and this maps to 0, 1 bijectively. Okay? Now we could go on for the inductive step, but just to improve the intuition, because we already did it for n equals 1, let's look at that case also. Okay, this is not formally necessary, but let's just check that we have also the second part of the inductive assumption. So what did we say that is true for n equals 1? For n equals 1, we have that I 0, 0, okay, I 0, 1, I 1, 0, I 1, 1 are non-empty closed intervals. And what is the what is is it true about the second part? So that F2 from I A0 A1 to 0 1 is a bijection. Is that true? So this is I00. What is the second iter of I00? What is F2? So what is the first iter of I00? Is I0. And therefore when you iterate once more, you get all of 0, 1. Right? So, and what happens if you take this? What is the first iter of this? Is I1. And therefore the second iter is all of 0, 1. Okay? And the same for these. Each one of these maps, this one here maps to I0, and therefore the next iter maps to 0, 1. And this one here maps to I1, and therefore the next iter maps to 0, 1. See, that's why I wanted to pass to this, because this is the simple we were getting. Trying to draw the picture sometimes can get very involved. It's worth doing it at home, but really the main observation is just simply that because of the way these intervals are defined, each one maps to the next level up, right? Because as a bijection. So I0 maps bijectively to 0, 1, I1 maps bijectively to 0, 1, and therefore when you look one more, when you include the zeros I00 and I01, by definition I00 maps to I0 bijectively, and because I0 maps bijectively to 0, 1, the second iter maps bijectively to 0, 1. So you get this structure, okay, where each of these is a bijection, okay, and then it becomes simpler. So we do not need to. What was happening before is we're trying to go to smaller scale and construct this. But now, if you have a bijection here, then what happens? So now, if we assume inductively that we have this case, okay, then how do we go to the next step? So by inductive assumption, f n plus 1 from I A0 to AN to 0, 1 is bijection. So what does that mean? What is the picture here? So that means that we have our interval here, I A0. By the inductive assumption, this is a non-empty closed interval. We have, let me draw a better picture up here. So here we have our little interval A0 to AN. And then we have Fn plus 1. And then we have 0, 1.
I or A?
Sorry. Okay, so how are we going to now construct the next level interval? So from this, we can then I A0 AN plus 1. So this is the set of points that are given where the orbit of the points x belongs to IA0, the image belongs to IA1, right? They follow the itinerary given by this particular sequence of zeros and ones. So we keep restricting, and then we take the little interval where you follow exactly that combinatorics, right? And now you know that when you iterate this Fn plus 1, it maps bijectively to 0, 1. And what is the structure of 0, 1? Well, 0, 1 has this delta image in the middle, and it has I0 here and I1 here. So what does that mean? That means that this interval here, we can chop it, and because this is a bijection here, it means there will be some smaller interval here, right? And either this maps to I0, and this maps to I1, or vice versa, depending if it's if it's orientation preserving, orientation reversing, and then we will have that IAN is equal to, we will have that AN 0 and IA0, AN1, okay, are disjoint, non-empty subintervals of IA0. Okay? Which is what we were trying to say here, but rather than pulling back and drawing smaller and smaller pre-images of delta, you just observe that actually if you, at this scale, if you take now the second iterate, you come back to 0, 1, and therefore inside here there is a subinterval that maps to delta after 2 iterations. And then you just repeat that process over and over again, right? So at this stage n, you know that this is a bijection, so there is a small subinterval that must map to delta, and the 2 intervals that are left would map to I0 or I1, and they give exactly those 2 intervals. Okay? So this proves the lemma, right? Because we've proved that for any choice, okay, this proves the lemma, because it shows that given your sequence, in fact, it shows a little bit more, right? What does it say? It shows exactly that you have it shows the lemma, because the lemma says that you have exactly as many such intervals as there are combinations of zeros and ones of that length. For every possible combination of zeros and ones, you have exactly an empty closed interval that has this property. Okay? And what do we know? So, to complete the induction, we need to show that now Fn plus 2 is a bijection on these intervals here. Is that true? Okay? Because if after Fn plus 1, this little interval maps to I0, then one more iterate will map it to the whole interval 0, 1. Okay? So there was one more step, non-empty subintervals I0, and Fn plus 2, so the next step of I0 to an plus 1, whatever that is, to 0, 1 is a bijection. Okay, so that completes the inductive argument and shows in particular that these are non-empty closed intervals. And moreover, they're nested, right? The construction shows that by definition they're nested. So by definition, if a bar is equal to some specific sequence, okay, then the interval I is 0 to an plus 1 is contained in IA0 an, which is contained in IA0 n minus 1, right, which is contained in IA0 because of the definition, because this is the set of points that are in A0, these are the ones that are in A0 that images are in A1, and so on. So we can take the intersection, let I of a bar equals the intersection overall n of IA0 an. And what do we know about this intersection? It's closed. It's non-empty. Why is it non-empty?
Because it contains one is 0.
Sorry?
This is contains the
Contains
Contains the fixed points. No, this does not contain any fixed points. So lemma I a bar is non-empty. And let's put it as this, and I a bar is a single point. The two independent statements. So non-empty
zero.
sorry?
Zero.
Zero.
No,
I think
no,
no.
this
Main
is
thing
a-
that the point is
Union of decreasing. Union of
Intersection.
intersection.
Intersection of closed sets, of nested closed sets, is always non-empty. This is general topological statement, okay? In this particular case, you can give a direct proof because these are intervals, right? So if it's a union of closed intervals, then the left-hand side of the interval is always less than the right-hand side of the interval. And so if you can take the converge, you must have a converging sequence of endpoints and another converging sequence of endpoints, and these two endpoints must be one less than or equal to the other, so they must give a non-empty interval, possibly degenerate, possibly a single point, but okay, in the particular case in which the nested sequences are closed intervals, then you don't need this general topological result, you can prove it directly, right? So IA is non-empty because it's a nested sequence of closed sets, nested intersection of closed sets. And why is it a single point?
Limits are equal, we need to prove this.
So is it always true that a nested intersection of closed intervals is a single point?
No.
No, of course not, right? Because you could have the interval 1 over n, 1 plus 1 over n. For example, 1 minus 1 over n. Sorry, no, I want the nested.
1/3.
0 minus 1.
Yes, so minus 1 over n, yes, thank you. Okay, so this is a strictly nested sequence, but the intersection is 0, 1. So how do we know that this...
The size of the interval.
The size of the interval, very good. We need to show that the size is going to 0. Because we know that at every finite level is a nested interval, so you have intervals, so the intersection is not only non-empty, but it's also connected. It's an interval, okay? So if the size is going to 0, then it has to be a single point. So why is the size going to 0? Let's figure this out and then we'll have a little break.
Each interval is 1/3. The length of each one is 1/3 of the length.
That's right, that's right. What is the length of each one? So, notice that the length of I0, length of A0 is equal to 1/3, and the length of A0, A1 is what? Why?
This is 1/3 of A0.
And why is it 1/3 of 1/3?
Because the map is 3x.
because the map is 3x, right? So the reason why I'm emphasizing this is because, as I said, I want to generalize this later. Okay, at the moment it's kind of easy, but the key point, the map is 3x, so everything is being stretched by a factor of 3, right? So if you have an interval whose image has length 1/3, then it will have length 1/3 of 1/3. Okay, so it's the pre-image. So to formalize that a little bit, we use the mean value theorem, basically, right? So this is equal to 1/9. Okay, more generally, so if x belongs to A0 to AN, okay, then, okay, as we said before, Fn plus 1 maps A0, AN to 0, 1 bijectively. And what is the derivative? And Fn plus 1 prime of x is what? 3 to the power 1/3 is 3 to the power n plus 1, right? Because the derivative is always 3 here, either 3 or minus 3, right? So by the chain rule, remember, by the chain rule you take the product of these derivatives, right? Remember, the chain rule are just, I mean, this is elementary, but because we are going to start using this a lot here, remember the chain rule says that the derivative of some x is just equal to the product of the derivatives, f prime in f of x, right, all the way to f prime in f minus 1 of x. The derivative is just the product of the derivatives along the orbit. Okay, because Fn is just a composition. So this chain rule is not usually written like this because you have f composed with g, but when f is the composition, you can check that that's what it means. Intuitively, the derivative is this. And here, therefore, this derivative is just the product of the derivative along the points of the orbit, and the derivative is always 3. Okay, either 3 or minus 3. So when you take the absolute value, this is just 3 to the n plus 1. Okay, and because for every point, so this is for all x in I A0 AN, okay, so we actually have a bijection from this to this with constant derivative, right? So this is I A0 to AN. This is Fn plus 1. This maps to 0, 1. And now we use the mean value theorem to get what? To get that this is equal to the derivative times this, right? And so by mean value theorem, we have that the measure of A0 to AN is equal to, in this case, well, less than or equal to in the mean value theorem, in this case equal to 1 over this, which is 3 to the minus n plus 1. Because when you multiply this length by 3 to the n plus 1, you get exactly 1, which is the length of this. Any questions? Are you okay with this? You okay? Was it? Yeah, you understand the mean, how I'm using the mean value theorem here, right? So the image of this, the mean value theorem says that Fn plus 1 of A is equal to the derivative in some point times the length of A. Right? So I'm just writing the length of A is equal to the length of the image, which in this case is 0, 1, in this particular case, divided by this derivative, which is 3 to the n plus 1. Right? And so the size of this, and this of course goes to 0. Okay? So in, and so they shrink to 0, and so they go to 1. let's take a 2-minute break, have a glass of water, and then come back. So, our conclusion is that, in conclusion, so let's So what does this I bar mean dynamically? So notice that IA bar is exactly equal to the set of points where Fi of x is an IAI for all I greater than equal to 0. So this is already more remarkable than it seems at first sight. What I'm saying is, I'm saying you give me an infinite sequence of zeros and ones, whichever one you want, and there is a point which has exactly that sequence. Its trajectory, right? I say there's a point in lambda that has exactly that pattern that spans, if you give me a sequence that has 1,000 zeros and then 1,000,000 ones and then whatever you want, I say there exists a point that does exactly that. It stays 1,000 times in I0 and then it moves to I1 and then it stays as many times as you want in I1 and then it comes back according to your stipulation. There is a point that does that. Okay, just to kind of emphasize what we've just done here. The richness. Okay, we're going to now look at it even more systematically, but already just by that it's quite remarkable. So where is this point, for example, that spends 1,000 times in I0? Can you tell me roughly where it's going to be? If it starts by spending 1,000 times in I0, can you see more or less where it has to be?
Very close to 0.
Very close to 0. Very close to the fixed point. Okay? Because when you continue, there's several ways, but when you continue this procedure, you see that actually I0, 0, this is going to be I0, 0, this is going to be I0, 1, and you see that you get smaller and smaller intervals that is just correspond to I0, 0, 0, 0. Okay? What is the point, what is the sequence that I need to end up with 0? If I take the sequence all zeros, if I do this procedure, and I choose as my sequence the sequence that has infinite number of zeros, then I get exactly the fixed point, the single point that this gives me. In other words, the set of points that stays in I0 forever is only the fixed point 0. Why is it only the fixed point 0? Besides the fact that we've proved this, but just looking at the map, can you see why it is the only point that can possibly stay in here forever? What happens if the point is not 0? Then the distance from 0 is growing all the time by a factor 3, right? If the point is non-zero, however small that, if it's epsilon away from 0, this little interval 0 epsilon is growing by a factor of 3 each time. You look at its image, it is 0 times 3 epsilon, then 0 times 9 epsilon, 0, and so on. It's growing, it's going, it's going, it's going. So this means that this point is moving further away, and eventually it's going to grow so far that it's going to land in I1. Okay, that point cannot stay in I0 the whole time. Okay? And so we have, okay, so this is just to get a better feeling for what's going on. So this means that for any sequence A bar, okay, there exists unique x in lambda, which has whose combinatorics, I write it in word, whose combinatorics in terms of whether the orbit is in I0 or I1, okay, is given by E. Any sequence. And the same argument that I just did shows that so what do we need to show now? For any sequence you have a unique point, and in particular this implies that 2 points cannot have the same sequence, okay, because we've just shown that given a sequence you get a unique point, it's the only point that can have that sequence, right? And so what we like to claim, let's see, do we need to say anything else? So let sigma 2 plus, okay, we'll say y, is equal to the set of all such sequences. A0, A1, A2, where AI is in 0, 1. Set of all infinite sequences of 0 and 1. Okay, then what we've defined here is a map. Let's write it as pi from sigma 2 plus to lambda, defined by sigma a bar is equal to I bar. This is well defined, right? Because we've just said for each a bar we have a unique point here. Is well defined. And we would like to say that it's a bijection. So what do we need to say that it's a bijection? So we need to say that it's injective. So why is it injective?
Because every sequence corresponds to different one.
Because any two sequences, because of what we've just said here. So if you take two distinct sequences, then they give each of these terms is the set of points that has exactly that same combinatorics. So two different sequences necessarily give rise, injective, yes, so they cannot give the same point, right? So no two points can have the same combinatorics. Okay? And why is it surjective?
For every point, you can have such sequence.
Because for every point, you can define its combinatorics. By definition, if a point belongs to lambda, then all its iterates belong either to I0 or to I1. Okay? Therefore, given any point in lambda, you define its combinatorics, and you use that to construct your sequence. Okay? And then once you've got your sequence, you define it this way, and that gives you exactly the point that you started with. Okay? So this is well defined and bijective. And this is the key now of everything, is that we have a dynamics on lambda, and we would like to define also dynamics on sigma 2 plus that corresponds to the dynamics on lambda. We want to construct a conjugacy. We want this to be a conjugacy between the dynamics on the two sets. Okay? So if you know the sequence, so if x is equal to I a bar, okay, for some a bar equals A0, A1, and so on in sigma 2 plus, then what is the corresponding sequence? Of f of x, i.e. if f of x is equal to b for another sequence, in sigma 2 plus, because both of these points are in lambda, so both of them has a corresponding sequence. What is the relation between the sequences A and B? Is there a relation between the sequences A and B? In other words, what is the combinatorics of f of x? We know the combinatorics of x. Remember, this sequence tells us the combinatorics. It tells us that x is in IA0, f of x is in IA1, f2 of x is in IA2.
So starting A, shift
Yes.
from A1.
So we're just starting, right, with f of x. So this sequence in the future must be exactly the same as the sequence A. Okay, it's just that we're starting here instead of here, because we're starting with f of x, which we know is here, and then everything else follows. Okay, so then this means that bi is equal to ai minus 1 for all bi plus 1 for all I greater than 0. Right? So this sequence here is actually exactly this sequence, but starting from A1. That means that B0 is equal to A1, B1 is equal to A2, and so on. B3 is equal to A4. And so on. Right? So we can define a map. Let sigma from sigma plus 2 to sigma plus 2 be defined by A bar goes to B bar, which is sigma A bar, okay, where exactly this condition, where Bi is equal to Ai plus 1 for all I greater than equal to 0. Okay, as you said, this is a shift in the sequence, and this is called a shift map. On the space of sequences. Is this a conjugacy? So we now have the dynamics. This is a shift map. We have a dynamics here. We have a dynamical system. Okay? So and this idea is a lemma, but it's really simple. So if you take, so we have, here we have sigma 2 plus, sigma 2 plus, here we have this shift map, and here we have f restricted to lambda, and here we have our map lambda. We have f restricted to lambda, which maps to lambda, okay? And then we have, for each sequence, we have the map pi that maps to each sequence the corresponding map, right? And as we said before, so then we have that if you take, so I wrote it like this because I always cannot remember, so the point is that if you take f composed with pi is equal to pi composed with sigma. So the lemma is that F is restricted to lambda and sigma are conjugate. And why is that? Because if you take sigma, so indeed sigma of A bar is by definition, okay, as we said, B bar, where, as we just wrote here, Bi is equal to Ai plus 1, okay, and therefore sigma pi of sigma A, okay, this is exactly, so if you take A is the sequence associated to a point X, then sigma A, as we said before, is exactly the sequence associated to f of X, so this is equal to f of pi of A, which is the point associated with A. Right. Just because of what we said before. By this observation here. So what does a conjugacy allows us to, what properties of the dynamics do conjugacies preserve? At the moment we've not shown that it's a topological conjugacy. We've not looked at this topology of the two sets, but we've just got a conjugacy. So we've got a set sigma 2 plus, we've got a set lambda, we've got dynamics on the two, and we've got this conjugacy. So remember, what are the structures that the conjugacy preserves? Not limit points. Limit points, you need the topological. Fixed points and periodic points. It maps always periodic orbits to periodic orbits. Okay? So now, when we look at the map lambda, as we said before, how do we find some periodic orbits? It's not easy to find some periodic orbits. But for the shift map, it's easier. So what are the periodic orbits? So what are the fixed points? So study, so periodic points for the shift map. So the shift map is very nice because it's very concrete.
Shift map is same as things.
Exactly. It's exactly the same kind of concept, right? So what are the fixed points for the shift map? 0, 0, 0, and 1, 1, 1. Right? So fixed points are 0, which is just the constant 0, and 1, okay, which is just 1. Periodic points, so these are fixed. And then periodic points, whatever. You take a 0, 0, 1 recurring is a periodic point. Right? So if you have 0, 0, 1, 0, 0, 1, 0, 0, 1, then okay, whatever it is, you map by sigma to 0, 1, 0, 0, 1, 0, 0, 1, and so on. Then you map by sigma to 1, 0, 0, 1, 0, 0. Okay, and then you map by sigma back to where you started. So this periodic orbital period thing. So suddenly, out of the blue, we prove that for our original map, lambda, we have periodic orbits of all periods. Right? Because here it's very easy to see. So you have exactly, in this case it's very easy. You see exactly all the periods. You've got exactly 2 fixed points. You've got exactly 4, well, you've got periodic points of period 2. You've got the 0, 0 recurring, 0, 1 recurring, 1, 0 recurring, 1, 1 recurring. Okay? So you've got 2 extra ones compared to the 2 fixed points, and so on. So you can count exactly how many periodic points you have for every period. In particular, you have every period, you have an infinite number of them. Okay. So this is again a really remarkable observation that this is the first step of this coding strategy. Okay, so I gave this example. In the next few lectures we will go further. We will show that in fact there is a topology on the space of sequences, and with that topology this becomes a homeomorphism, and so we have a topological conjugacy, and then we're going to look at whether this has some dense orbits, and they will map to dense orbits here, so we will look into more detail. Okay, but the very first step is that what we've done is we've taken this system like this, okay, which basically looks like this, and we know that a lot of points escape, okay, but with this simple coding, basically by saying all the points that don't escape, they must lie either in I0 or in I1, okay, and this coding mechanism, the fact that we can show that actually for every this simple argument that shows that you can code all the points by all possible sequences of zeros and ones, and because you're doing the coding dynamically, you actually get this conjugacy, and then suddenly you know, okay, there's actually infinitely number of periodic orbits of all possible periods. Okay, so this is a kind of a remarkable strategy to get a lot of information from something where really you cannot see directly the periodic orbits in there. Any questions? Okay, so this was the first steps in symbolic coding and symbolic analysis. Thank you. So I'm going to go and talk to Patrizia unless you have anything, any objection. I would like to schedule an extra class next week. So we have one more class tomorrow, right? And then next week, at the moment there's only one scheduled. I would like to schedule two because I would like to finish, because then I'm going to be away for 10 days. We have a kind of longer break. So I would like in these next 3 lectures to finish this part of the course, rather than leave one last part. Is it okay for you? That would have to be either Monday, Tuesday, or Wednesday next week. Okay? Okay, so we'll try to do
Is
that.
it possible to do it this week?
Sorry to do it, well, but this week we have...
Friday, I'm not sure.
Oh, on Friday.
I'm not sure on Friday.
We have no.
Is Friday good for you? Friday is good for me.
Because
I'm not right
next week another hour is going.
Okay, yeah, if you prefer, we can do Friday, it's perfect for me. Okay, so we'll ask Patrizia. So there should be the availability if there was another course scheduled, right? You're saying there was another course on Friday? Okay, perfect. I'm good in that I asked. So then we'll do it on Friday, and then we'll just do one next week, and then we'll finish this part of the course. Okay, thank you. Take care.
Very nice.
It's all the
Huh?
It's all the
No, I think so. I only saw 2. Next homework. It's just 11 problems.
Oh, did you know?
When the simulation date?
Next